Okay, so I'm here to discuss considerations for reducing weld fume with the GMAW process. Going to discuss welding variables, filler metals. There's a lot of things that come into play when discussing weld fume. So I have to have my standard disclaimer here. Every big business requires it. Basically what this says is just every welding environment is different, and there's no one-size-fits-all approach. An industrial hygienist is really going to be your greatest tool in helping decide the path that you take to mitigate weld fume. But this presentation should give you some ideas to hopefully start from. So basically there's three big regulating and advisory bodies. There's the ACGIH, which is the American Council of Government Industrial Hygienists, and what they do is they look out for research, and they make recommendations based upon the research that they find. I'm not sure how many of you are familiar with their current notice of intended change with manganese, but that's a recommendation. Then there's OSHA. Obviously, pretty much everyone here is going to be familiar with them. They create and enforce regulatory standards. And then there's NIOSH, who conducts scientific research, develops guidance, and authoritative recommendations. So this is just for total weld fume overall. OSHA currently does not regulate weld fume as a whole. Now that doesn't mean they don't regulate weld fume, they just regulate it through its constituent elements singularly. They have different levels set for different elements, such as manganese, nickel, things of that nature. NIOSH has a recommended exposure limit for weld fume and total particulate, but it's pretty broad, with being the lowest feasible concentration. And then the ACGIH has actually assigned a weld fume TLV, which is what they call a threshold limit value, and that's 5 milligrams per cubic meter as a total weight average for a normal 8-hour workday. So OSHA has kind of mandated some steps towards reducing your weld fume. It's kind of broad, but it essentially breaks down into these three steps. Your first step is engineering and work process controls, which fall into process and behavioral changes. And then you have engineering and work practice controls again, but that's more isolation and ventilation. And then you fall into the PPE and respiratory protection. My friends from Miller earlier already discussed a lot of the ventilation and things of that nature, so I'm going to stick to the process and behavioral changes for this presentation. The first step, obviously training. It seems very simplistic, but it's a very easy and cost-effective way to just initially reduce your weld fume concentration that's in your welder's breathing zone. Typically they'll take a collector and they put it right there in the welder's breathing zone. If you can get your welder to keep his head out of the weld plume, obviously they're going to collect a lot less fume there. So, I mean, that's one way to go. Advising your welders how to position themselves so that the dust and particles don't accumulate inside the welding hood. Also following instruction on manufacturer's recommendations for operation, as well as instructions on MSDS's and AWS's Z49.1. So I want to go a little bit into sampling and reporting. Air sampling is typically completed to a method that's NIOSH 7300 type. It utilizes a 0.8 micron multicellulose ester filter, and the results are a time-weighted average. Now these are reported in milligrams per cubic meter. And what that means is they send it out, it goes through, they dissolve the filter actually in acid, and there's a really long name that I cannot pronounce, intraphoton spectroscopy or something, that they analyze for the specific elements and determine the weight in milligrams. And then the air pump that they use pulls in so much air, and they figure out how many cubic meters of air comes in, or they've pulled through that filter, and that's where they come up with that milligrams per cubic meter. Now manufacturers such as Miller, Lincoln, Hobart Brothers, we can't do that because every application is different. So for example, one welder in this room is obviously not going to have the milligrams per cubic meter that 40 welders in this same room with a higher arc-on time might have. So how do we quantify that to know whether we can offer a lower fuming solution or not? And what we do is we follow testing that's completed according to a laboratory method. And AWS F1.2 is the laboratory method for measuring fume generation rates and total fume emissions. These results are typically reported as grams per minute, and that's what I'm going to be referencing throughout the presentation. Now, while that doesn't correlate directly to milligrams per cubic meter, you can see obviously that if you can reduce your grams per minute of particulate, that obviously you're going to reduce your total weld fume. So first off, we have weld process selection. So globular transfer mode is typically not the most stable of processes, and it's undesirable in applications where weld fume is a consideration. Because of this, shielded metal arc welding and self-shielded flux cores are generally not the most desirable when considering a process where fume is a concern. Gas-shielded flux core bridges the gap between globular and spray transfer modes, and they typically have less emissions than the shielded metal arc welding and the self-shielded electrodes, but they still aren't as good as the GMAW process in the spray transfer mode, which is solid wire and metal core type applications. Now, one thing I get a lot of questions about is pulse, GMAW pulse. It can reduce your fume, but to make a blanket statement is impossible on that. Many pulses nowadays are adaptive, such as Miller's AccuPulse. I think Lincoln has something like that. And because these pulses adapt to changes in the welding environment, you don't know what's changing inside that machine, so quantifying the effect that it's going to have on your weld fume is impossible. On top of that, you can't just make the blanket statement because there's a number of manufacturers out there that offer pulse, and they all have their own proprietary waveforms, and no one really knows how they're going to affect their process without being able to look at these proprietary waveforms. So this is just a quick little graphic that kind of shows the typical fume ranges in grams per minute of the different processes. And then the second consideration is material condition. This is one that tends to get overlooked a lot, but blasting or grinding to remove mill scale prior to welding can significantly reduce your weld fume. Also cleaning base materials to remove greases and oils. If you order a cold rolled material, typically they'll have some sort of rust preventative grease or oil on it. That can affect your weld fume and cause it to go up. As you can see in, as you can see in this graph here, the blue is the blasted material, and that's significantly less than the hot rolled material, which has heavy mill scale on it. Now, you also want to verify the chemicals added to the material prior to welding. As I mentioned, oils, greases, things like that. are not good for it. But what many people overlook are cutting fluids, rust preventatives, things like that. Here you can see more graphs with a study done that shows various different cutting fluids versus no cutting fluid, and various different rust preventatives versus no rust preventative. And then here it goes on to show that different anti-spatters can also have effects as well. So these can be considerations when choosing things outside of your welding process that you can look at that may help potentially reduce your weld fume. The next consideration is shielding gases. Argon CO2 mixes are more desirable for CO2 in flux cord applications where welding emissions are concerned. Generally, CO2 is not the most desirable for welding fume in your shielding gases. So you'd like to use richer argon blends. 9010 is a good one, but it's also been shown that oxygen and helium additions as well can help reduce that weld fume. So switching up to 95.5% oxygen may help reduce weld fume as well. I'm Kevin's company, Praxair. They have some nice proprietary mixes that probably work as well too. So here's just a graphic. This is solid wire showing different fume generation rates for different shielding gases. So as you can see, the 9010 falls far below the AC25 and the AC15. And this is just another graphic showing different shielding gases with a flux core wire. You have 100% CO2, which is showing the highest, and then you have 75% argon, 25% CO2, which is significantly better, and then you have a proprietary trimix that contains a small amount of helium, which has also helped reduce weld fume slightly. The next consideration is filler metals. Emissions characteristics of wires of the same classification can vary drastically, whether it's from product to product or manufacturer to manufacturer. As you can see here, you have manufacturer 1A and 1B. Those are actually the same manufacturer, but those are different products in that same ER70S-6 classification. As you can see, they vary pretty significantly, and then manufacturer 2 and 3 vary even more significantly from that. So not everything is equal in filler metals. However, many manufacturers offer low emissions alternatives in their product line to drastically reduce emissions. The blue line there shows a low fume metal core, which is actually producing lower weld fume than solid wire, but then you see your standard metal core can produce significantly more fume than solid wire. And that's just looking at a couple different wires there. You could cover that entire graph with different manufacturers and products, and they would all vary significantly. Diameter also comes into play. The diameter should be chosen so that the desired amperage range is towards the top of the operating range. As you can see here, these metal core wires, this is the same product, different diameters. It drops significantly towards its operating range. 045 is typically the top end's considered around 325 amps. Here you can see it drops around 280 and I've seen it'll keep decreasing slightly, but then you also see this with the 052 and the 062 in these graphs. So now we're going to discuss welding parameters a little bit. The AWS F1.2 laboratory method is says arc length is a major controlling variable in fume generation rate. And arc length's a function of many factors, but there's really three main ones that come into play. You have your arc voltage, your wire feed speed, which amperage correlates to that, so amperage has an effect as well, but for the purpose of this discussion, we're just going to say wire feed speed. And then you have your contact tube to work distance. So for lower voltages, higher wire feed speeds, the graphic there shows X, which is lower voltages, higher wire feed speeds, and longer contact tip to work distances will give you that shorter arc length, and then higher voltages, lower wire feed speeds, and shorter contact tip to work distances will give you that longer arc length. And as you can see here, these are the same. We kept the wire feed speed the same for the same product and increased the voltage, which is effectively going to increase your arc length. And as you can see, the fume generation rates trend upwards. And here you're getting into wire feed speed and amperage. If you can keep the voltage the same and drive up your wire feed speed and your amperage, you can see that trends your fume generation rates down. And you can also see, if you were watching at Weld, you could see that your arc length is going to drop significantly as well. And then here is just another graphic showing the different voltages and how you see the trends with the wire feed speed and amperage that drop your arc length as well. Now the other thing to consider is that all of this being equal, you're feeding a lot more wire into the system at those top ends. So you're actually converting less of the wire into the fume. So your fume generation rate is less, but you're putting down more wire. So less of that wire is going up into fume. Some weld process modification considerations. A lot of this could be tough to implement in your facility for a number of reasons. You may not be able to modify existing welding procedures. You could be bound by contract or a pre-qualified procedure, or it just may be too expensive to qualify your welders or a new procedure. You could also, I discussed the material condition, the blasting, the grinding. Those are additional operations that can add to cycle time. And then you've got weld quality considerations whenever you begin adjusting your weld procedure. And then there's also the consideration that even though you may change all these in your weld procedure to help reduce your fume rate, it may not be enough to ensure your compliance. So it's not a one-size-fits-all approach. The welding emissions are affected by virtually every variable in the welding process. The differing environmental conditions are going to, in your applications, are going to cause things to swing significantly. So your best route is to get a qualified industrial hygienist who can help you work through all of the potential solutions and find the best one for your company. He'll also help you quantify everything so that you can actually see the benefits. Now, one thing I do want to talk about a little bit is when you reduce weld fume, it can be a bit of a balancing act. Now, I discussed earlier that OSHA doesn't regulate weld fume as a whole, they regulate the constituent elements. What happens is when you reduce your weld fume, let's say we jacked up the wire feed speed and the amperage like you saw in that graph earlier, and we significantly reduced your fume. Amperage has an effect on manganese, and that can drive up the percentage of manganese in that weld fume. Now, so it's a balancing act because even though you've reduced your weld fume, you've driven up the percentage of that weld fume being manganese, so you still may or may not be in compliance with those specific elements. And so that's a consideration that needs to be given as well.